Hi, we're The Gap, the group assessing the problem. Our members are Morgan Hoffman, Timothy Gillikin, William Stremecki, and Sophie Minnick. Our FEDD project was to design a collapsible bridge.
As a group, we used the engineering design cycle throughout the whole process of the design of our bridge, and it ultimately helped us create the best project we could under our specific constraints. For the ask portion of the design cycle, we used the project outline provided to identify the constraints we had to work with, including the maximum weight of 5 pounds and our $40 budget, which are the constraints we believed we would have the most trouble with. For the research portion of the process, we used books from the library and some online sources to gather information on various bridge designs and how they actually function. We also discovered what to avoid when constructing our bridge. For the imagine part of the cycle, we got together as a group and brainstormed some different design concepts for our bridge. We also investigated different materials that we could use on our bridge, including various types of wood and metal alloys. For the plan portion, we decided on an arch-shaped bridge design and used Autodesk 3D modeling software to design and scale a prototype to our likeness. We then determined that we would construct our bridge using wood, metal chest latches, and steel cables. For the create part of the cycle, we began construction on our first prototype, but after we fabricated all of our wooden pieces, we realized there was a huge flaw in our design. This sent us back to the drawing board to come up with a new concept for our bridge. And for the last step, the improve step, we created a new design and modeled it in Autodesk again. In doing so, we managed to save some components from our previous design, and after construction and assembly, we concluded that our design should work.
Earlier in the video, most of the design challenges and constraints of our project have already been discussed. We will touch lightly on some of the more pressing issues again. Our greatest struggles were in attempting to design the bridge to be 5 pounds or less, and being cut appropriately to allow for both collapsibility within a cubic foot of space and ease of assembly across 5 feet. As a result, the original design we settled on was an arch bridge cut into 7 pieces that would have latches connecting each segment to the others and a tension cable to balance longitudinal forces along the span of the bridge. In theory, this original design was great except for the flaw that became evident the more we considered how forces were being transferred along the arch. Because in our original design, we had our central piece, which is a trapezoid, long base side down, we realized that none of the other pieces were positioned underneath it to help carry the load of the bridge effectively. Plus, this design would overstress the latches between the sections sooner, as they would already be trying to cope with varying components of force along the arch. Following this discovery, we tweaked our design to what it is on the right side of this slide in order to allow for the central piece, our capstone, to have better vertical support from the other sections of the bridge. Undoubtedly, while these changes cost us time and materials, it was worthwhile considering the risk of premature collapse before we hit 60 pounds. Thus, we salvaged what we could, like the central piece, which we merely flipped over and adjusted accordingly. In the end, our design was able to comply with every constraint except that one requiring the bridge to be 5 pounds or less.
During our research, we found that there are 5 main bridge types, including beam, arch, suspension, truss, and cable stay. 2 important components of a bridge include compression and tension forces, and they are different depending on the design. Construction is very important because a minor detail can cause a huge failure. Finally, symmetry is very important for a successful bridge.
At competition during FEDD, our bridge officially weighed in at 5.5 pounds. It could be assembled in around 45 seconds, spanned the required 5 feet, and held 111 pounds out of the required 60. Sadly, our bridge failed at the latches we used to secure each piece of wood together, meaning it could have held the maximum weight with stronger materials. After the results from all the bridges came in and points were tallied, our bridge won honorable mention for its performance. Following is a video of our bridge during competition.
Reflecting on the competition, we would definitely change a few things. First, we would choose lighter and more uniform pieces of wood to avoid being over the weight limit. We would invest in stronger fasteners so they would hold more weight. We would model our bridge in CAD so that the dimensions would be easier to cut. We would reserve wood shop slots well in advance to avoid time crunch at the end. And finally, we would have made sure we had access to a more precise scale before competition to avoid being unsure about the weight.
Finally, we have some advice for future groups doing the Collapsible Bridge project. It's very important to start planning early so you can spread out the workload and avoid rushing at the end. Our group met weekly to discuss upcoming deadlines and our next steps in completing the project. We recommend creating a schedule and sticking to it, as this will help you keep from procrastinating. Our group did a good job managing our time for the most part, except we should have left more time in the last couple weeks before FEDD for assembling the bridge. We tested our bridge the day before FEDD, which was risky, but thankfully it worked and there were no complications. Sharing the workload is also important since there are a lot of components to the FEDD project, including research, the project charter, and building the bridge. At each of our weekly meetings, we made sure to discuss who was responsible for what jobs, and this teamwork allowed us to complete all parts of the project by the assigned deadlines. Finally, make sure to take advantage of all resources available on campus. We spent a lot of time in the craft center woodshop, cutting our wood, adding latches, and drill pressing holes to complete our bridge. The resource room in Daniels was also very useful since we got free supplies for our poster presentation. Project gurus and your TAs are also great resources, so don't be afraid to ask any questions you might have about the project. Hope this advice helps. Good luck on your Collapsible Bridge.